In the 60s and 70s, two American jetliners dominated the world airliner market. They were the Boeing 707 and the Douglas DC-8. One, the iconic 707, even had a popular song written about it, which became an international hit. Both airliners used a similar modern swept-back wing and four-jet layout that was considered extremely advanced for passenger planes at that time. As this duo of American commercial successes did so well, it is often overlooked that a third U.S. company, Convair, had also entered the fray, and its airliner might have been the fastest of them all. One of the most common expectations for jet aircraft is that they are fast. Though jet airliners also fly smoother, higher, and are quieter than other passenger planes, their most powerful feature of all is that they are faster. So it is perhaps logical to assume that in the competitive world of airlines, the fastest jetliner would also be the best. And if you were the Convair Aircraft Company, which were equipping the U.S. Air Force with both fighters and bombers that could fly at twice the speed of sound, it is also a reasonable assumption that their jetliner offering would indeed be the fastest in the air. The 990 Coronado. She was the most beautiful airliner of her time, and certainly the fastest. Ron Strauss recalls the 990's phenomenal speed flying in and out of Berlin for modern air transport.
When we flew the corridor in Berlin during the Cold War at 10,000, the Russians controlled the airspace. So we had to be down before the boundary. Lots of times on descent, we'd get the 990 up to 0.912 Mach, which was really fast. In fact, it would get going so fast that we'd get a vibration in the fuselage, and lots of times it would suck the nose gear doors open, so we'd just put the gear handle in the up position that repressurized the landing gear, and we'd go that way until we crossed the boundary.
The 990. She was not only fast, she simply made her competitors, the 707 and the DC-8, look just bland. Although she almost bankrupted her maker, the giant Convair, with the largest write-down in U.S. history. During World War II, numerous aircraft companies excelled in designing different types of warplanes. Although in America, most four-engine land-based planes originated from just 3 companies, at least when it came to quality and quantity. They were Boeing with their B-17 and B-29, and Consolidated with their B-24, all 3 of which were heavy bombers, and Douglas with their C-54 large transport. After the war, Americans were eager to indulge in more leisurely pursuits, and they began consuming a plethora of new technologies and products. Instant cameras and microwave ovens brought the promise of a more carefree future. The airlines and aircraft manufacturers recognized that travel would become an important part of the lives of Americans, freed from the restrictions of rationing and the obligations of war. Aircraft that had delivered death were suddenly delivering passengers to sunny destinations. Post-war, the C-54 soon became known as the civilian DC-4, followed by the DC-6 and the DC-7, in an ongoing stream of stretched but excellent passenger planes. The B-29, after conversion to a military transport, the Stratofreighter, later saw airline service as the Stratocruiser. This was a useful airliner, although it never enjoyed the success of the Douglas propliners. Another interesting post-war airliner development was Lockheed's superb Constellation airliner. Though it had almost been overlooked in wartime production, it re-emerged as a peacetime winner. In this period of transition, Consolidated, which soon became Convair, seemed to abandon large propeller transport aircraft with the exception of a single example, the largest type ever made, the experimental XC-99. This monster proved that extremely large aircraft could be made, although only one ever was. So 3 proven U.S. propeller-driven airliners came to dominate the post-war civilian market. The extremely successful Douglas series of C-54s, which always seemed to be getting longer, Boeing's less-than-stellar Stratocruiser, and Lockheed's revitalized Constellation. For a decade, these sturdy types led the world in establishing passenger air transport for business and pleasure, and to an extent never previously dreamed of. These mainstays of the era's airlines were all straight-wing types, and so too were their military counterparts. Even the first-generation post-war fighters and bombers, many of which were jet-powered, shared the same cruciform shape as wartime propeller-driven types. Aircraft like the 6-engine Martin XB-48 would have been typical of the time. Then, suddenly, all that changed. Allied countries gained access to advanced German designs, including a number developed in their 1,000-kilometer-an-hour wind tunnels. Within this cache of advanced data were conclusive facts that proved aircraft could fly safely, much closer to the speed of sound, by using the assistance of a swept-back wing. However, there were risks with the swept-back wing, risks the military were prepared to take for more speed, but it was still a tough sale. Boeing was one of the main champions of the swept-wing concept. Their XB-47 Stratojet had both wings and tail sections fully swept. Later production versions could reach speeds exceeding 600 miles an hour. Unfortunately, low speed handling was poor, and jet fuel consumption was very high. Nevertheless, over time, hundreds of Stratojets would go into production, though they would all require some form of regular in-flight refueling for their critical missions to be successful. This disadvantage of poor low-speed handling would prove very problematic, because all of the Air Force tankers at that time were Boeing KC-97s, straight-winged, piston-powered aircraft which were close relatives of the less-than-successful Stratocruiser. The incompatible nature of the two aircraft was brought home by the fact that the B-47s had to drop down to dangerously low speeds and altitudes to couple with the slower tankers. The Air Force needed a swept-wing jet tanker, and nobody knew that better than Boeing. Whilst the swept-wing revolution was underway, in the military, Douglas and Lockheed were quite happy to maintain their existing product lines. Fairly regular upgrades of their base products provided something new to sell, with a comparatively small increase in cost for the buyer. And if a major rework was to come, it need not be so radical as a brand new pure jet with swept wings. Rather, a straight wing configuration able to support the new jet turboprop would represent sufficient progress.
In the 50s, there was quite a different mindset. The general view was that turboprops were going to be more useful in long haul because they were less thirsty and therefore they could build them with longer range. You had aircraft like the Lockheed Electra and the Bristol Britannia occupying the turboprop routes. And they did a pretty good job on the whole on some quite long routes. You can't forget El Al used to serve Tel Aviv, New York non-stop with the Bristol Britannia, which is, again, unthinkable today.
The turboprop was a safer as well as a more economical aircraft to fly than pure jets. The proof of this could be found on the other side of the Atlantic in Britain, with the thoroughly successful Vickers Viscount, a medium-range type that sold in the hundreds to a worldwide market. With its 4 Rolls-Royce Dart turboprops, there was nothing to compete with the Viscount's speed and comfort. Even more support for similar turboprop airliners came when Vickers announced the development of an expanded Viscount, the Vanguard, and Bristol Aeroplane began production of the Britannia. All three used fairly conventional layouts and economical jet-driven propellers. Douglas were totally in favor of the straight-wing prop jet philosophy. Apart from anything else, they were smoother and faster than earlier piston types, and with straight wings, just as easy to land and take off. Later, Lockheed also looked to the straight-wing turboprop formula, and eventually committed substantial funding to design and produce their Electra turboprop airliner. However, the 1950s saw life continue to speed up for consumers. The newly invented credit card made it easier than ever to spend. Ray Kroc franchised McDonald's, kicking off the fast food era. Even the music of the time was faster with the birth of rock and roll. Did consumers have the same need for speed when it came to air travel? A visionary leader at Boeing realized the first company to meld speedy jet engines with passenger planes would dominate the airliner market. Not all companies were eager to develop jetliners. Lockheed continued to make Constellations right up until some airlines were actually ordering pure jets, and they never offered one of their own, preferring to go the way of the smaller turboprop, as defined by Douglas and practiced by the British. However, Boeing, which was hardly established as a major supplier to the airliner business, saw a chance to utilize its vast experience with jet bombers to produce tankers for in-flight refueling and ultimately jetliners. As more jet bombers came online, Boeing knew a jet tanker would be required, so using their own money they developed an aircraft that could serve this function, and also perhaps that of a jet passenger aircraft. The president of Boeing, Bill Allen, knew that if he could sell his tanker to the Air Force, much of the cost of a new passenger aircraft would be reduced, as much of the R&D would be shared between both projects. This was a very brave gamble. Douglas, with its long-standing relationships with many of the world's airlines, based on hundreds of past sales, would have been well connected to launch a successful new jet airliner to compete with Boeing, although it had never actually planned to create one so soon. Boeing quietly produced its Dash 80 prototype that might serve both military and civilian masters. There was little choice but to sweep its wings and to use pure jet power, as it had to keep up with similarly equipped Air Force bombers. The civilian version, too, benefited from this technology. In 1954, when the U.S. Air Force announced that, on the strength of a single privately funded Dash 80, it would order several hundred swept-wing jet tankers, Douglas was totally shocked. Boeing had scored a major win from the military. However, to Douglas, the major threat lay in the possibility that Boeing might convert its new KC-135 tanker into a pure jet airliner and skip right past the planned Douglas straight-wing turboprop airliners. The Douglas response was to rush forward with plans for their own pure jet passenger liner. At first, the four-jet swept-wing DC-8 seemed to have a reasonably promising future. After all, for years, the company had done so well selling earlier DCs to clients all around the world, something that Boeing had never been able to emulate. And now, with Lockheed going in another direction, they should have an even greater advantage. Inevitably, Boeing soon announced their passenger jet, the 707, and very importantly, Dash 80's development was well underway while the DC-8 lagged behind.
Boeing and Douglas were certainly more adventurous, with going straight for the jet, swept wings, potted engine configuration. And of course, they must have realized that the jet engines that they started with would not be the jet engines they would finish with. So the development forced the efficiencies in the jets by Pratt & Whitney and General Electric and others, and Rolls-Royce. So the 707 and DC-8 did become transatlantic airplanes with great non-stop capabilities as a consequence. And once they got into service, the others didn't have a chance.
It was into this competitive turmoil that Convair decided to enter the large passenger jet business. From a strictly commercial point of view, the company did have an edge. Like Douglas and Lockheed, they had cultivated a long list of airline relationships virtually on every continent, although theirs was a shorter range product, the CV-240. Originally envisaged as a replacement for the Douglas DC-3s, 240s evolved into a major commercial success with nearly 1,200 examples produced. Often known as the Convair liner, the new aircraft offered such features as tricycle landing gear for greater passenger comfort and safety, a pressurized cabin, as well as a built-in air stair avoiding the need for outside steps. The Convair liner's financial success was well recognized by Convair shareholders. However, by the mid-50s, sales of twin-engine piston-powered airliners were slowing down. The latest upgrade, the 440, was starting to be less competitive in its class.
The Convair 240, which became the 440 Metropolitan, which eventually became the 580 when they installed turboprops. All three aircraft were good aircraft. They survived very well in service with the airlines who loved them. And as a matter of fact, even today, the Convair 580s are still in service in secondary roles, for instance, firefighting. Of course, its economics started to suffer in airline service from about the late 60s.
Knowing this, Convair's commercial business division was starting to look for other products to sell to its much-prized client list. The fact that its only real post-war commercial venture had been a replacement for the pre-war DC-3, and its competitor had consistent experience with large four-engine airliners, seemed not to matter. In one single step, Convair's offering went from an early post-war propeller-driven short-range aircraft to a sleek, extremely fast four-engine swept-wing jetliner, and a good-looking one at that. A true vision of speed and beauty, perhaps the biggest leap forward for any commercial manufacturer of that time. But how did Convair think they could possibly achieve advantage over such established large transport competition? And how would the Convair jetliners compete against 707s and DC-8s? Their answer was with greater speed and perhaps a little more style. Nothing as radical as the Concorde of almost 2 decades later, although perhaps going just a fraction in that direction. Well, if in 1955 Convair's civil airliner division looked a little slow, just across the way at Convair's military aircraft division, things were anything but. The Cold War was ensuring that the U.S. Air Force had a steady demand for all types of aerial weaponry, including supersonic jet fighters and bombers. The F-102 Dagger advanced fighter was an aircraft designed around a new delta wing shape. The Dagger's purpose was to be the new backbone of American defense against Soviet bombers. By necessity, it would have to be thoroughly supersonic. It also had to carry the latest missilery. At one stage, its communication system became so sophisticated that the aircraft could be totally controlled directly from its ground base without the aid of the pilot. Still, even with all these advanced electronics, the first prototypes actually had trouble even breaking the sound barrier. Greater attention had to be applied to a new type of aerodynamics before it could fly at Mach 1. For all that, the Dagger was produced in large numbers and was later developed into the Mach 2 106 Dart, an aircraft which is generally considered one of the best defense interceptors of the Cold War. Another Convair highly advanced delta wing product, the Mach 2 B-58 Hustler, was also developed from the mid-50s onward. The Hustler was the United States' only dedicated supersonic plus jet bomber to go into full production. With 4 powerful General Electric afterburning jets, Convair's B-58 could fly as fast as any fighters of the time. Convair learned much about very high-speed flight with the Dagger and the Dart. But the Hustler also taught lessons in high speed with large aircraft, all of which the company expected to find very useful as it approached the problems of making a modern jet airliner for the first time. .880s went into production just as the 440s were coming off the line. It was hoped that one old successful product would simply be replaced with a new one. A major feature of the latest one would be its speed. .880s were expected to fly in excess of 630 miles an hour. Much of the reason for this speed was the fact that its 4 jet engines were civilian versions of the very power plants that powered the supersonic B-58 jet bomber. Only the .880 would not have the afterburners critical for the Hustler's remarkable Mach 2 ultimate top speed. Other points of commonality certainly would not be overlooked by the marketing staff of Convair or any of the airline clients. An interesting irony is that the B-58 was intended to replace the B-47, the very aircraft that Boeing used to spawn the swept-back wing concept and set the standard for nearly all jetliners to follow, including the .880. Given that Boeing and Douglas were both aiming for the long-range international market, Convair could see wisdom in designing their jetliner more for the medium-range intercontinental market. Although as a safeguard, there was a provision for extra fuel tanks to be fitted in the midsection of the wings. If really necessary, this would provide for a range of 3,250 miles, which would make it competitive with the early 707s and DC-8s, although the Convair aircraft would be carrying less passengers. At the time that the first swept-wing jetliners were evolving, it was generally accepted that seating in the coach section would be 5 across. However, in Britain, a competitor to the U.S. designs was evolving in the form of the Vickers VC-7. It had a swept-wing shape, 4 jet engines, and one feature that gave the American company something to think about. Its one major advantage was that it had 6 seats across in coach, 3 on each side with the center aisle dividing them, offering a more balanced look to the cabin and a greater number of seats for the airlines to sell. As soon as U.S. manufacturers became aware of Vickers' approach, Douglas and Boeing immediately committed to a radical and expensive widening of their jetliners. Evidence of this change can still be seen in Boeing's tankers.
It's not well known today, but the fuselage of the military version, the C-135 and the KC-135, is in fact narrower than the civilian 707. And the reason was that Boeing wanted to get 3 and 3 seating configuration in economy to get the squeeze in the maximum number of passengers.
Though Boeing and Douglas were anxious to make the seating change, Convair deliberately retained their narrower fuselage in the interest of greater speed. As it happened, the VC-7 never went into production, although it probably had as much impact on the evolution of future airliners as any aircraft ever had. It would take 2 years and 9 months from the start in April '56 to first flight in January '59 before the first .880 was finally ready to enter the 4-jet passenger market.
During the early 1900s, as America began to emerge as a global power, Roosevelt delivered a prophetic statement on international diplomacy, advising to speak softly but wield a formidable presence. 50 years later, amid the United States' role as the foremost defender against communism, its formidable tool was undoubtedly the Convair B-36, a long-range bomber. Although this immense aircraft served predominantly throughout the 1950s, its origins can be traced back to before America's entry into the Second World War. The B-36 earned itself the unofficial title of Peacemaker. By 1941, the United States Army Air Force had 2 effective heavy bombers in its arsenal. One was the renowned B-17, crafted by the Boeing Company. This exceptional 4-engine aircraft played a crucial role throughout the war, with later heavily armed versions aptly dubbed the Flying Fortresses. A slightly later addition to the fleet was the consolidated B-24 Liberator. Featuring an advanced tricycle undercarriage allowing for swifter landings, the Liberator served in all theaters of the war. Moreover, its larger, sturdier fuselage facilitated conversion into transport planes, rendering the B-24 one of the most adaptable aircraft in the American infantry. The Liberator, like the 17, was also heavily defended, and it was also able to fly slightly higher than the Fortresses. However, more significantly, it boasted extended range, making it frequently utilized for maritime patrol missions, covering then what were considered significant distances solely on internal fuel. Both the B-17 and the B-24 could only complete the journey from America to Europe one way. In 1941, the Army Air Force had also commissioned another bomber, envisioned to surpass its predecessors in altitude and distance capabilities. Another creation by Boeing, the B-29 Superfortress stood out as the most formidable bomber deployed throughout the entire conflict. Despite several hundred being ordered, not a single prototype had taken to the skies. As a secondary contingency plan, in the case of any setbacks with the B-29, the consolidated B-32 Dominator was proposed. While this aircraft wasn't produced in large quantities, it did offer a reassuring alternative to the Superfortress's remarkable capabilities. However, by 1941, it too existed only on blueprints. By the middle of that year, Nazi Germany had conquered continental Europe, achieving successive victories. Of greater importance, despite Britain's partial air superiority, it endured relentless bombardment from the Luftwaffe, causing significant devastation to both its populace and industry. These raids, often conducted at night but sometimes during daylight, were perceived by the German High Command as means to subdue the island nation. The pressing question that American tacticians grappled with was simple. What would occur if the U.S. entered the conflict and the sole remaining Allied base in Europe fell to Germany? One option American strategists explored was the development of an aircraft with such extraordinary range that it could take off from bases on the American East Coast, cross the entire expanse of the Atlantic to deliver its payload, and then return to continental America without the need for refueling or fighter escort. The American aviation industry had previously created long-range bombers. Among these was an early Boeing endeavor, the XB-15. This aircraft boasted a wingspan of nearly 150 feet, requiring the full power of its four 1,000 horsepower engines to hoist its 35 tons of bulk into the air. The second experimental long-range bomber was developed by the Douglas Company, and the prototype XB-19 was ordered in September 1936. Upon completion, this aircraft boasted a wingspan of 212 feet, surpassing the XB-15 in size. The endeavor required 500 men, 9,000 drawings, 2 million man-hours, and $1.4 million of military funds, ultimately exceeding Douglas's original budget by an estimated $4 million. Undoubtedly, developing colossal aircraft proved to be a costly endeavor. Nevertheless, the XB-19 represented a significant milestone in aviation standards, not just in terms of size, but also in innovation. It was the inaugural aircraft to feature a retractable tricycle undercarriage and was designed to incorporate power-operated guns and a turret. If it had entered production, it would have boasted a range exceeding 7,000 miles. The insights gleaned from the XB-15 and XB-19 projects, coupled with the recognition of deficiencies in the aircraft inventory of the early 1940s, and the looming prospect of waging a European war from the American shores prompted the American Defense Department to address the challenge of producing an ultra-long-range heavy bomber capable of making a round trip across the Atlantic. To tackle this, it solicited designs from Northrop and Consolidated. The Northrop design was notably unconventional. The premise behind it was that eliminating the drag effect of the fuselage and tailplane could significantly enhance range. Thus, Northrop embarked on designing an aircraft essentially compromising only a wing, a flying wing. Consequently, on October 25, 1941, an order was placed for 2 XB-35 experimental bombers. The Consolidated design was more conventional than its competitor in shape, but certainly not in size. Featuring an expansive wing area of just under 5,000 square feet, the B-36 necessitated no fewer than 6 engines positioned at the rear of the wing to propel its colossal 163-foot fuselage through the air. On November 25, 1941, an order was sanctioned for 2 aircraft, with the expectation that the first would be developed by mid-1944 at a fixed fee of approximately $800,000 each. However, the much-needed bomber bases in Britain remained available to the Army Air Force, allowing the standard B-17 and B-24 heavy bombers to commence attacks on enemy targets from 1942 onward. Deployed in abundance, the Fortresses and Liberators exacted a devastating toll on the enemy. The demands of a Pacific theater, particularly after the seizure of the Mariana Islands in mid-1944, were capably met by Boeing's B-29, which provided the Air Force with the means to strike deep into Japan's heartland. Yet, it was a specific B-29 armed with a particular bomb that ultimately brought the Second World War to a close, marking the culmination of much military aircraft development. 2 notable exceptions to this narrative were the experimental long-range bombers, ordered only 2 weeks before American involvement in the conflict but never afforded sufficient priority until the war's conclusion, alongside the necessity to deploy a new weapon unforeseen in the wildest dreams of tacticians 4 years earlier. The inaugural Northrop B-35 was actually assembled in an open environment and finalized in June 1946. This clever design, which was the source of controversy for many years, was powered by 4 pusher engines and was intended to carry a crew of 9 in the pressurized center section, for its shape barely allowed the word fuselage to be applied. Despite its innovative design, which featured flaperons on the end of each wing instead of a conventional tailplane, the radical new shape of the flying wing was never able to completely overcome stability issues. Nevertheless, the flying wing stands as one of the most ingenious aviation concepts in history. The first XB-36 was rolled out of the experimental hangar just 6 days after Japan surrendered. However, it wasn't until August 1946, nearly 5 years after it was ordered, that the Peacemaker was ready for flight. The prototype's single main wheels were an impressive 100 inches in diameter, making them the largest ever produced for an aircraft. However, this feature would later prove to be a significant weakness. The 6 pusher-type engines were designed with air intakes located on the forward section of the wings. However, this advanced concept for its time also encountered initial difficulties in cooling the engines and would necessitate later modifications. On August 8, 1946, the first XB-36, commanded by a Captain Burial A. Erickson, taxied down the Fort Worth runway with a total crew of 9 and 8,000 gallons of fuel. At precisely 10 minutes past 1 in the morning, Ericsson lifted Convair's colossal aerial masterpiece into the air for the first time. It was the largest plane ever to take flight. The flight lasted no more than 37 minutes, during which the undercarriage remained in the wheels-down position as a safety precaution. Ericsson's crew, on this occasion and many subsequent ones, subjected the giant aircraft to rigorous testing, swiftly identifying the challenges inherent in its immense size. One of the most significant challenges was the vibration generated by the immense engines spaced out across the wide expanse of the wing. Cooling, particularly at high altitudes, presented another issue. It was evident that the numerous areas would require substantial attention. However, perhaps the most fundamental challenge was the sheer size of the wheel arrangement, which restricted the Convair bomber to runways at least 22 inches thick. Given that only 3 such runways existed anywhere in America, it was clear that a solution needed to be found swiftly. The solution emerged in what was deemed another breakthrough, combining 4 56-inch wheels into a group under each wing. This arrangement spread the B-36's tremendous weight over a much broader area, allowing the Peacemaker to utilize runways of half the previously required thickness. Early in the B-36's development, Convair recognized the potential of leveraging its enormous wings and tailplane for the transport version of the Peacemaker's commercial counterpart, the XC-99, which conducted its maiden flight in November 1947. Still, larger again than its bomber counterpart, the 99 was assembled at Convair's San Diego operation, but with wings and other common parts shipped across the nation from Fort Worth. Here at Lindenberg Field, the aircraft that had now earned the title of the world's largest was now poised to showcase the potential that would later inspire the development of mammoth transport and airplane concepts in decades to come. The XC-99 garnered significant attention from Pan Am, which seriously contemplated a civilian version for the West Coast to Hawaii route. The airline even secured options on 3 such aircraft. However, the anticipated post-war airline boom failed to materialize for many years. The XC-99 never entered civilian service. The sole example produced remained in active duty with the Air Force until 1957, proving particularly invaluable during the Korean War, where it expedited essential payloads across the nation. Though this aircraft required modification with a new undercarriage system, once implemented, it proved remarkably versatile and had the capacity, if needed, to transport 400 fully equipped troops. However, it was ultimately ahead of its time. Despite the XC-99's intriguing potential, Convair's primary focus remained on the extra long-range bomber concept. Throughout the late 1940s, Convair continued to refine and develop the B-36, underscoring its unparalleled ability to strike virtually any target worldwide and return to base in America. Long range would require many hours of physical endurance for the crew, and therefore inside the 36's massive fuselage, adequate provisions were made for sleeping quarters and a galley, complete with a 2-burner stove. Adequate provisions were always ensured for the crew aboard the B-36. However, the center pressurized section, housing these amenities, was located a considerable 80 feet away from the forward control area, accessible only via a narrow tunnel spanning the distance. Heated food was packaged in specially designed containers for transport between the extensive distances of the 2 pressurized sections. Additionally, the tunnel served as the sole means for personnel to move between crew sections. Given the distances involved, a small trolley was provided to facilitate efficient movement for each member. The size of the B-36 also necessitated unique procedures not previously required by other aircraft. Immediately after takeoff, and before pressurization, a crew member was tasked with examining certain vulnerable areas within the massive interior structure forming the fuselage of the B-36. Only then would the plane be permitted to climb to higher altitudes and proceed with its mission. Numerous other challenges stemming from the sheer size of the B-36 also surfaced. There was a pressing question regarding how to service each of the massive aircraft, which was so large that special outdoor hangars had to be constructed to provide access to only the essential parts. Despite successful resolutions to the problem of engine vibration and cooling, there were undoubtedly serious concerns about the viability of the B-36 compared to other alternatives. Foremost among these was the upgraded competitor, the Flying Wing, which had transitioned to an all-jet aircraft by replacing its 4 propellers with 8 turbojet engines. Northrop aimed to enhance the speed and viability of its innovative concept, utilizing unique flaperons at the wing's end to compensate for the absence of a conventional tailplane. Another, more conventional competitor to the B-36 emerged from the past, the Boeing B-50. Essentially a standard superfortress from the Second World War era, the B-50 featured more powerful engines and extended range due to the underwing-mounted fuel tanks. This range was enhanced yet again by Boeing's successful development of aerial in-flight refueling. Thus, the Air Force had at its disposal a proven aircraft combination capable of flying the same range as the B-36, but without encountering the challenges of its immense size. By the late 1940s, due to these advancements, the future of the B-36 appeared increasingly bleak. Its salvation came through 2 significant developments. The first, poetically enough, was provided by Consolidated's long-term competitor. Boeing developed a successful medium-range bomber entirely powered by jets, leveraging captured German technology that demonstrated the advantages of a swept-back wing. The Boeing B-47 featured a wing not only swept but also remarkably flexible, capable of moving within an arc of 17 feet. To maintain a thin wing profile, the 6 engines had to be mounted in pods suspended from below. The outer pods each contained 1 engine, while the inboard pods each housed 2 engines suspended several feet below the wing's surface. Engineers from both companies collaborated to attach this equipment to the outmost wing of Boeing's aircraft. With 6 turning and 4 burning, the B-36 finally began to transition into the jet age. The other event, which was sure to secure the future of the 36, took place on June 24, 1948, when the Soviets closed the gate on Berlin, signaling in one step the beginning of the Cold War. The escalating concerns about communism culminated in an event that jolted the West out of its post-war complacency. NATO forces suddenly found themselves facing a formidable adversary, and the need for an intercontinental bomber swiftly transitioned from hypothetical to urgent reality. At this juncture, no aircraft in the world possessed the long-range capabilities of a Convair giant. Rather than canceling orders, demand for the Peacemaker actually increased. As apprehension persisted, the significance of America's Strategic Air Command, responsible for long-range bombing, grew substantially. It was ultimately placed under the direct command of General Curtis LeMay. LeMay boasted an impeccable record from World War II, beginning with his early involvement in European bombardment with the Army Air Force and continuing through his command of Pacific operations in the B-29 bombardment of Japan. Regarded as one of America's great wartime strategists, he also oversaw the Berlin airlift. Given his extensive experience, LeMay was deemed the most qualified individual to elevate the Strategic Air Command, including its rapidly expanding fleet of B-36s, to the highest level of readiness. Under LeMay's unwavering leadership of SAC, the American public found reassurance in the knowledge that although they no longer held a monopoly on atomic weaponry, they possessed arguably the most formidable platform for delivery, the B-36. Such was the military's concern for safeguarding its intercontinental bomber that security measures were heightened to a wartime level. Personnel in SAC-controlled rooms were required to carry firearms despite being hundreds of miles within American borders. The protection of America's formidable asset necessitated even mechanics servicing the engines to carry firearms while at work. Exercises were conducted at an increasingly intense pace, around the clock and in all weather conditions under LeMay's leadership.
Out, this is engineer. Engineer's checklist complete. Ready for takeoff. Over. Pilot checklist complete. Ready for takeoff. Roger, give me 100% on the jets. Roger. Jets coming up. Engineer, give me full power. Full power coming on. Jets 100%. Tailpod tempo okay. Takeoff power is set. Everything stabilized. Engineer ready for takeoff. Roger. Carswell Tower, Air Force 653, ready for takeoff. Air Force 653, Carswell Tower, roger, clear to roll. Roger, 653, rolling. Here we go. Give me climb power. Roger. Climb power coming on. Give me 96% on the jets. Roger, 96% on the jets.
Often flying individually rather than in formation, SAC's peacemakers practiced bombing raids over vast distances with minimal notice. The B-36s utilized the K-1 bombing navigation system for precision accuracy. This sophisticated system comprised 365 vacuum tubes, enabling the B-36 to conduct bombing runs at high speeds regardless of weather conditions. Targets typically consisted of radio signals emitted from special trucks designed to assess the accuracy of SAC's aircraft. Despite the hefty price tag of over $5 million per aircraft, coupled with the K-1 system and LeMay's insistence on relentless training, the combination ensured nothing short of exceptional accuracy.
Pilot, this is radar. We're over the IP. Pick up a heading of 197.
Bob Flight Air Force 653, over the IP. Altitude 35,000, on an inbound heading of 197 degrees. Flight Air Force 653, 30 seconds to go. The bomb's away. 15 seconds to go, bomb flight. Code switch coming on. Bombs away.
Despite the remarkable potential of the Convair giant, critics often raised concerns about its large size, which could potentially make it a prime target for enemy fighters. Even before the first B-36 took flight, the Air Force ordered a unique auxiliary, the McDonnell Goblin, intended as a parasite fighter to be carried within the B-36. This extraordinary design was stripped down to the bare essentials and featured fold-down wings that allowed the aircraft to be fully concealed within the B-36's bomb bay. While it was never actually deployed with the Peacemaker, its flight controls were operated from a B-29 mothership, and flight trials began in 1948. In August, with test pilot Ed Scorch secured in the cockpit, the Goblin was launched by a trapeze mechanism from the B-29, and the pilot successfully flew what must be considered one of America's most remarkable fighters. However, upon attempting to reconnect the Goblin's hook to the trapeze, turbulence caused the little fighter to lift, and the mother's plane mechanism broke the canopy, wrenching the oxygen mask away from the pilot. But Scorch was just able to regain control and crash land this tiny fighter. This setback did not stop development. The second and only other Goblin produced continued its assigned task. Eventually, on October 14, 1948, a successful hookup was achieved, and the Goblin was pulled up into the B-29's belly. However, despite the bold concept, the bomber-fighter-parasite combination was never adopted, as it seemed to pose as many problems as it attempted to solve. Nevertheless, a later parasite project involving the B-36 was the Phycon concept. This program commenced in 1952 and entailed mating a Republic F-84 directly underneath a modified Peacemaker. Unlike the previous concept, there was no intention of fully enclosing the F-84 within the mothercraft. Only after both aircraft were airborne would the fighter pilot enter the cockpit. Together with the highly trained boom operator positioned in the mother plane, they would undertake the delicate task of lowering the fighter using a large hydraulically operated boom to a point below the bomber where the fighter could be safely released. This operation proved remarkably successful, and although the recoupling process demanded great skill, it was eventually perfected to a fine art. The combination of these aircraft provided many potentials, especially as the pilot was able to come and go from the fighter when it was in the docked position. In reality, the Phycon mission was primarily intended to enhance the reconnaissance capabilities of the B-36. The F-84, whether in its straight or swept-wing configuration, was an incredibly versatile aircraft. While SAC utilized it as its own fighter aircraft, there's no denying its potential as an effective fighter bomber, as demonstrated during the Korean War. Given SAC's ability to transport such versatile aircraft thousands of miles to the very edge of enemy territory, coupled with the simultaneous development of small, compact nuclear weapons, it's conceivable that SAC could have employed its Phycon combination in a bomber role. By the mid-1950s, the B-36 was fully developed and deployed at various SAC bases across the nation. By the early 1950s, SAC's Peacemakers had reached the pinnacle of their development, with early engine and vibration issues resolved. With the support of jet power and modifications such as the new quick-action bomb bay door, the B-36 personified the ultimate intercontinental atomic bomber of the era. Despite the technical success of the project, it continued to face political and inter-service criticism. As early as 1949, there was an investigation into the political influences surrounding the B-36 that would ultimately yielded no significant outcomes. However, the Navy's resentment toward the Peacemaker was more pronounced and perhaps more justified. The cancellation of its promised 65,000-ton supercarrier, which was intended to deliver atomic attacks on potential Soviet industrial centers, was partly attributed to the Air Force's insistence that the B-36 represented a more flexible deterrence strategy rather than the eggs-in-one-basket philosophy of a carrier. Equally significant was the SAC's assertion that it could operate just as effectively from the edge of enemy territory under conditions that would be unattainable for naval aviation. To demonstrate this, B-36s would periodically fly from their central USA bases to the very edge of Soviet territory. Highly trained crews comprising pilots, navigators, radio operators, engineers, and gunners would endure for long hours of flight, often at very high altitudes over thousands of miles to the frozen wastelands of Alaska. These men understood that once in the Arctic region, should their aircraft fail and crash land, as some did, there would be minimal chance of survival in the sub-zero and uninhabited wilderness. Against these prospects, the roar of the Peacemaker's 6-piston and 4-jet engines must have sounded far more a blessing than a curse. The Navy's criticism of the Peacemakers persisted, reaching a point where they formally requested the Air Force to allow them to test its defensive capabilities against Navy fighters. Outwardly, the B-36 appeared to have minimal defensive armament. However, hidden beneath sliding panels, it concealed 6 remotely controlled turrets, each equipped with 2 20mm cannons. These turrets could be raised hydraulically as needed. When used in conjunction with the forward nose turret and radar-controlled rear turret, the B-36 boasted a total of 16 cannons, covering every approach within a range of over half a mile. This made the Peacemaker the most heavily defended aircraft in aviation history. Eielson Air Force Base in Alaska was a point to which many B-36s on exercise would travel. Here, Peacemaker captains would land their massive aircraft, uncertain of the prevailing weather conditions as they made their approach. For some, the landing functioned much the same as their departure point thousands of miles away. However, for others following closely behind, visibility could be near zero, pushing the pilot's skill and determination to the limit. Even in this environment, where weather conditions offered as much protection for grounded aircraft as they posed risks for those in the air, anti-aircraft protection remained abundant. Under this protection, ground crew would immediately begin servicing the landed aircraft. For these men, the journey from aircraft to heated bus was not a short one, and they had to adapt the hostile environment as best they could. With efficiency, the aircraft would be refueled by crews working on the icy wing surfaces, mindful of the potentially fatal consequences of a fall. With padded clothes and gloved hands, these ground crews took perhaps a difference, but nonetheless, a real risk as those who flew. With time always passing, each engine would be assigned its own crew member to conduct necessary checks before inclement weather set in. The extreme cold of the region meant that if aircraft had been idle for more than a brief period, the engines would require additional heating, primarily through the large air intakes, to prevent them from freezing solid. To address this, large mobile heating units were developed, capable of delivering significant amounts of hot air into and around all the piston engines. The crew compartment also received similar treatment, not only to ensure habitability, but also because instrumentation and onboard equipment would not function effectively in such frigid conditions. Refueled and ready for departure, the B-36s would once again brave the cold Arctic sky on their journey southward, leaving the area to its natural inhabitants. However, the primary purpose of these exercises was to demonstrate that from Alaskan bases, it would be just as feasible to turn northwest towards Soviet territory and deliver the devastating cargo for which the B-36 was developed. Another type of cargo was also identified. Convair, which designed the 36, won the contract for the Air Force's first supersonic bomber, the B-58 Hustler, which was the culmination of Convair's long involvement with the Delta design. Moving an as-yet unflown bomber from base to base proved to be challenging of a task until a temporary solution was found, mounting it under a standard B-36 with its two inboard props removed, protecting the wingtips of the newcomer. This image perhaps symbolizes, above all else, the contrast between two generations of aircraft. In less than a decade, the pursuit of a faster bomber aircraft had radically altered their shape and size, to the extent that tomorrow's medium bomber could fit snugly beneath yesterday's heavy bomber. Clearly, the era of giantism was drawing to a close, yet Convair still harbored hopes for its mammoth aircraft in an upgraded form. In response to the Air Force's requirement for an all-jet heavy bomber, the company developed the YB-60. Hopes were high at Fort Worth in April 1952 when the YB-60 made its first public debut. Continuation of the production line would secure the jobs of thousands of staff and subcontractors, bringing added prosperity to the city that had produced the world's largest bomber. The YB-60 was virtually a B-36, with fully new swept wings and a tailplane. With no defensive armament other than the rear turret, the entire rear crew and quarters were omitted from the YB-60. Enhanced power and reduced weight propelled the YB-60 to a top speed of just over 500 miles per hour. Its production was achieved rapidly, as 70% of its components were standard to the B-36. The Air Force ordered 2 such examples to test the concept, but only actually flew one. On August 14, 1954, at a ceremony at Convair's production line in Fort Worth, the last B-36 was handed over to the Air Force. The final delivery from the Peacemaker plant must have been a bittersweet moment for the people of Fort Worth. Although Convair would continue to utilize the plant for many successful projects, it was from this base that they had produced, for many years, the largest plane ever to fly. A plane that many would argue, due to its sheer size, helped win a war without having to engage in combat.
The F-106 is designed to be a fully capable, highly effective, all-weather interceptor for use by the United States Air Force Air Defense Command units. Deliveries to these units will start in 1959. The tactical versions of the Convair F-106A single place and the F-106B dual place are supersonic Mach 2 aircraft powered by the Pratt & Whitney J75 P17 engine. Both carry their armament internally, with basic armament for each consisting of 4 Falcon missiles and 1 MB-1 nuclear rocket. Test activities for the year 1958 involved detailed testing of all elements of the weapons system, from laboratory testing of components to an extensive flight program. The F-106A and B Accelerated Development Program involved 42 aircraft, of which 17 were assigned to the contractor portion of the test program. This film report will present the significant highlights of the 1958 program. For the purpose of this report, the program will be divided into 3 sections. The first, or flight test section, will concern those activities covered in the actual flight program. The second, or support testing phase, will involve those component activities investigated through laboratory-controlled examinations. And the final armament section will report on the development program designed to demonstrate F-106 armament delivery capability. At the Air Force Flight Test Center, in-flight examinations included evaluations of the F-106 external wing tanks, F-106A spin testing, J-75 engine evaluations, and the initial flight and preliminary flight test evaluations of the F-106B aircraft. Early in the year, aircraft 56-451 was assigned to the spin program. This program was conducted to determine the stall and spin characteristics for F-106A aircraft. Aircraft 451 received all special spin equipment installations at Convair San Diego Experimental Facility before being returned to Edwards Flight Test Center for the flight program. Recovery strakes installed on each side of the aircraft could be extended during a spin to assist in spin recovery. A spin recovery chute was installed in a special container mounted at the base of the vertical fin. Used as a secondary safety precaution against spin conditions, this device was activated by ballistically firing a pilot chute into the airstream, pulling the recovery chute behind it. Special pilot safety equipment included a single-action ejection seat and a modified G-suit to protect the pilot against longitudinal G-loads in the event of high spin rates. All equipment was thoroughly tested in flight examinations to ensure proper performance before beginning the spin investigations. A total of 31 spins were made, beginning with preliminary spins in April of 1958. Initially, recovery was made before a fully developed spin was reached. Later spins were allowed to progress until the full spin was accomplished. During these developed spins, a condition was encountered where the airplane would gyrate after stalling. This condition came to be known as a post-stall gyration. Detailed examinations of this condition determined its cause, the warnings preceding it, and the proper recovery technique necessary. Analysis of the data obtained in the spin program demonstrated F-106A compliance with the applicable Air Force specifications. Following completion of the spin program, aircraft 56-451 was stripped of all special spin equipment, provisions were added to carry external fuel, and a program was conducted to clear all F-106A and B aircraft to carry and use the external drop tanks. At the completion of tank installations on the aircraft, ground shake tests were made, clearing the aircraft for flight flutter testing at the Air Force Flight Test Center. These tests were satisfactorily completed with full tank loads at altitudes of 5,000 and 15,000 feet. Speeds were at Mach 0.75, .85 and .95. During jettison testing, 9 tanks were expended, 7 single-tank jettisons, and 1 dual jettison. Altitudes were at 15,000 and 35,000 feet. The drops were accomplished at 2 different speeds, Mach 0.4 and 0.95. At the conclusion of the program, external fuel usage testing was completed on aircraft 452 up to a speed of Mach 0.95, with altitudes ranging to 40,000 feet in climb, dive, and level flight conditions. As a result of this program, sufficient data was obtained to clear all F-106A and B aircraft to carry and use external drop tanks. During the 1958 test program, several changes were made in the F-106 propulsion system to improve propulsion and aircraft performance. Thinning of the external inlet duct cowlings resulted in a satisfactory drag improvement. The slotted ramp replaced the earlier perforated ramp. This change increased pressure recovery due to improved bleeding of boundary air and resulted in a 3% increase in thrust. A flight program to determine optimum ramp scheduling for the new slotted ramp established ramp operational standards for all production aircraft. 5 tail cone configurations were evaluated in a program consisting of 22 flight missions. The original cone, shortened by 4.6 inches, resulted in an effective combination of drag thrust improvement. Improvements in ejector design led to the acceptance of the convergent divergent ejector, with the resulting thrust increase of 8% at design speed over the basic engine configuration. The Pratt & Whitney J75 P-17 engine was accepted for all F-106 aircraft over the earlier P-1 and P-9 versions. This engine included all basic improvements made in the earlier models. Rotating of the first stage inlet guide vanes and thinning of the second stage inlet guide vanes increased the flow area and resulted in relieving of low-energy stalls. First stage turbine inlet guide vanes were changed to a new alloy with heat characteristics that allowed higher operating temperatures than alloys used in earlier models of the J75 engines. The results of the propulsion program have confirmed the compatibility of the F-106 airframe and the J75 P-17 engine. These improvements have raised installed engine thrust and temperature limits to design specification requirements. F-106 aircraft, in which all of the new modifications have been incorporated, have now flown at the design speed of Mach 2. The first F-106B aircraft, 57-2507, moved off the production line at Convair, San Diego, during the early part of 1958. The aircraft was then delivered by truck to the Air Force Flight Test Center, and after thorough ground checkout evaluations, made a successful first flight on April 10th. The F-106B is designed to be a fully capable two-place interceptor aircraft with a complete F-106 armament system. It will serve as a tactical aircraft and, in addition, be used to familiarize pilots with the F-106A weapons system. Similar in appearance to the F-106A, the F-106B has a longer and slightly raised canopy. Dimensions are equal to that of the A. Wingspan, 38 feet, 1 inch. Overall length, 70 feet, 8 inches. Height to the tip of the vertical stabilizer, 20 feet, 3 inches. The approximate takeoff gross weight with full internal fuel load is 34,600 751 pounds. As a result of the similarity between the A and the B, the 1958 B flight test program was primarily devoted to examination of the significant differences between the two aircraft. Preliminary results have demonstrated that the F-106B maintains the same excellent handling characteristics of the F-106A. Climb and acceleration performance is essentially the same, with general performance in other areas comparable to the F-106A. Thorough testing of the complex electronic cooling and air conditions systems of an F-106 aircraft would be impractical using normal flight test methods. Necessary instrumentation and time would be very costly to the development program. For these reasons, an electronic cooling test stand laboratory was built at the contractor's San Diego testing area. The test stand chamber will hold an entire F-106 fuselage and is capable of recreating both transient and steady state temperature and altitude conditions for the entire flight range of an F-106 aircraft. Temperature can be varied from minus 60 degrees to 220 degrees Fahrenheit. The test stand method produces the data and development information necessary in proving the F-106 electronic cooling system adequate to the great demands made on it in actual flight operation. Changes in the F-106 cooling system, when proved necessary by test stand investigation, are incorporated into production aircraft following retest approval. A brief flight program confirms test stand results. The data available from this testing would be impossible to obtain without the test stand facility. The resulting savings in cost and time have proved invaluable in the F-106 development program. The skin of the 9 fuel tanks dispersed throughout the wings and fuselage of the F-106 are designed to withstand thermal stress as well as stress due to internal tank pressure and flight loads. The contractor established the Point Loma Structures test site in conjunction with the Air Force to test the effectiveness of the machine-sculptured, Scotch-weld-bonded tank skins. The jig work, electrical, fuel, and hydraulic systems here are adequate to subject fuel tank test specimens to a full range of simulated flight conditions. The tests conducted were on 3 tanks: the forward wing tank, the wing transfer tank, and the fuselage tank. Each tank was placed in its own special jig to most accurately apply flight loading conditions. All internal and external flight load conditions encountered in the full range of operation of an F-106 were mechanically produced through whiffletree and hydraulic actuator arrangements. Both static and extensive cycling loads tests were conducted through varying temperature conditions ranging from sub-zero through ambient to hot. Reduction of the data recorded from thermocouples, strain gauges, and other instrumentation determined that the machine-sculptured integral Scotch-weld wing tanks met design requirements. For the purpose of developing a high-efficiency F-106 radome, a special research and design group was formed within the electronic section of Convair San Diego as early as September 1955. Primary mission of the group was the development of a high-efficiency radome for the F-106. The basic concern was to design a radome which would allow efficient passage of the radiated energy search beam, and to ensure that the radar waves would complete passage through the radome with as little distortion as possible. The ideal radome would be electrically transparent, causing no radiation distortion. Since this is impossible, The distortions of the best possible radome must be measured and compensated for. To back up the design predictions based on this theory, the radome laboratory tested many radome experimental shapes with their complete test facilities. Bore sight range, direct physical measurement, high temperature dielectrometer, free space interferometer, and other complex equipment were employed. From this background of research and testing, the Convair radome design group has developed a radome shape and manufacturing technique which meets the demanding performance requirements of the F-106 fire control system. The technique has resulted in two major conclusions. One, it has reduced the insertion phase difference, or IPD variation, from 10 electrical degrees to 1. And two, it makes practical a method of reproduction with high physical standard from part to part. In addition, engineers can now predict electrical performance in terms of known radar properties and can maintain electrical variations within extremely narrow error tolerances. Matched to the gimbal of the MA-1, the radar antenna is individually bore-sighted to ensure accurate installation, and final checks are made before the delivery of the aircraft to the Air Force. With these newly developed design, development testing, and manufacturing methods, a very high degree of accuracy has been obtained in this vital component of the fire control system. With today's interceptor aircraft pressing farther and farther into the range of supersonic speeds, the need and urgency for developing a pilot ejection system that will function at subsonic, transonic, and supersonic speeds at minimum and maximum altitudes is vital. In view of this, the Industry Crew Escape Systems Committee was formed to coordinate a developmental approach to safe ejection from supersonic aircraft. First considerations included both an upward ejection system and a downward ejection system. The Air Force assigned Convair the responsibility of developing the needed upward ejection system for Century Series aircraft. In Convair's program, two types of seats were originally considered: the A, or skip flow generator type, and the B, or bobsled type. After initial evaluations, Convair, with the approval of the ICESC committee, concentrated its development efforts on the second, or B, seat design. The pilot is ejected on his back at a 90-degree launch attitude, a launch position especially desirable because G-loads tolerances for humans are greatest at this angle. Preliminary wind tunnel and slingshot testing of a 1/10th scale model led to a full-scale wind blast program at the Air Force Flight Test Center. These runs were used to indicate the wind blast forces on the seat and pilot. In all, there were 5 runs conducted at speeds of 627 to 858 knots. Both low and high altitude flight gear was examined for wind blast results. In all post-run examinations of this test series, the pilot and his personal equipment was found to be in near pre-run condition. The first full-scale aerodynamic testing of the B seat was accomplished on the ARDC Supersonic Missile and Rocket Track at Hurricane Mesa, Utah. 3 objectives were accomplished in this test series. 1, the full-scale seat-simulated ejection performance as planned. 2, the validity of the slingshot tests were verified by the flight attitude of the seat. And 3, The test confirmed the results of the previous wind blast tests on the pilot and personal equipment. It was established that the seat configuration had good yaw and pitch stability, but did have excessive roll. At this point, telescopic booms were added to control the roll. Following slingshot evaluations, further testing at Hurricane Mesa using the new booms resulted in near-perfect seat flight, with no pitch, no yaw, and with only a negligible roll. During 1958, testing of the complete B-seat ejection system was conducted on the sled run track at the Air Force Flight Test Center. Speed for this series ranged from 132 to 750 knots. Results of the program to date have demonstrated that the B seat, as developed, will provide a reliable upward escape system for today's supersonic aircraft pilots. To date, this is the only type seat that has been successfully ejected from a sled-simulated aircraft cockpit at supersonic airspeed, and remained aerodynamically stable and maintained accelerations within human tolerance. The sled tests showed that the configurations were stable over a speed range extending from 132 to 750 knots. It is felt that the operating principles of the B seat may be extended to much higher speed while maintaining good low-level, low-speed performance. In 1959, the B seat will go into hardware production for installation in tactical F-106 interceptor aircraft. Initial F-106 armament phases and test programs are conducted at the Missile Development Center at Holloman Air Force Base, New Mexico. The activities here have fallen into two general categories: those involving Convair armament subsystems testing, and those involving a joint contractor Air Force effort to harmonize the overall system. The Convair aircraft, numbers 458 and 460, were engaged in MB-1 ejection and ballistic studies and Falcon missile launching evaluations. The MB-1 ejection and ballistics program comprised a series of tests to demonstrate the compatibility of the unguided nuclear warhead rocket and the ejection system of the F-106. Prior to any live firings from an aircraft, inert rockets were ejected under various flight conditions. These tests determined rocket separation characteristics, but indicated that at a high Q condition, the rockets had high nose-up characteristics. This was corrected by a baffle and a 2-inch shorter stroke for the aft gun. Live motored rocket tests were made next to obtain clearance of the F-106A flight envelope. To date, MB-1s have been ejected on this program at speeds from Mach 0.9 to Mach 2 and over an altitude range of 10,000 to over 50,000 feet. The MB-1 ejection launcher proved efficient and highly reliable through repeated firings. The AD program, or Armament and Aircraft Weapons Control System Development Program, is a joint effort among the Air Force, Convair, Hughes, and Douglas. Among the primary objectives of this program was the flight operation of the highly advanced fire control system, the MA-1, designed and built by Hughes Aircraft. This MA-1 system is composed of many subsystems, each in itself a complex system: search and tracking radar, digital computer, communications system, navigational aid components, landing system aids, automatic flight control systems to be activated when cleared, and the armament auxiliary equipment. The MB-1 manual firing phase was started in December of 1958. 3 successful firings were made at an altitude of 20,000 feet and at a speed of Mach 1.25 against manned targets. The AD program provided the necessary changes required to give proven capability to tactical type F-106s in manual mode MB-1 firings. The accomplishments of the F-106 all-weather supersonic interceptor in its armament and in all flight testing to date has lived up to every design prediction.
August 6, 1945. The day warfare changes irreversibly. It is not the result of a battleship or a fighter plane. Instead, it comes from a device less than 10 feet in length and 3 feet in width. Dropped from a B-29 Superfortress, the bomb known as Little Boy is the first atomic weapon to be used in history. Alongside its accomplice, Fat Man, these two weapons of mass destruction pulverize the Japanese as 2 cities are obliterated. Now, the world led by the United States and the Soviet Union enter a new and frightening age where just one bomb can wipe out an entire population. With the Second World War ending and the Cold War beginning, America and the Communists start a massive buildup of this new technology. The race is on, where whoever possesses the most deadly arsenal of atomic force prevails. On both sides of the Iron Curtain, nuclear weapons become the ultimate symbol of strength and might. And during this period of intense Cold War anxiety, the idea of having aircraft fueled by this new source of energy is given the green light. If a nation can power homes and submarines with nuclear power, will planes be next? Having an atomic reactor on board has endless possibilities. Unlimited range, and the ability to be anywhere in the world in a matter of hours, ready to strike. Truly awesome aviation that will determine the #1 superpower. Unfortunately, this concept is easier said than done. Placing a nuclear device on an aircraft is both complicated and extremely dangerous. Can American scientists and aircraft designers overcome these obstacles? Can they prove the skeptics wrong? This is their story. The United States' decade-long saga to produce the first nuclear-powered aircraft. Prepare to experience the atomic-powered plane.
We are gathered here, representatives of the major warring powers, conclude a solemn agreement whereby peace may be restored.
With the Japanese surrender on the USS Missouri, Americans are both victorious and confident. The war they have been fighting for over 3 years has finally ended. They have emerged a superpower with what seems to be an unlimited industrial capacity. The nations of Europe are no longer the power brokers they once were, for it is the United States and its ally the Soviet Union that remain strong at the end of the Second World War. But just as this conflict ends, a new and more deadly struggle begins, as Nazism is replaced by communism as the greatest threat to Western democracies.
Nobody really knew a grand vision for Europe, even as Nazi Germany collapsed. There were still large questions as to territory, peoples, the movement of peoples, and exactly how this would all work out. The grand strategy with Franklin Roosevelt's the famous spheres of influence, which means nothing, everything and nothing at exactly the same time. And that's where the roots of the Cold War come in big. There was a lot of tension and a lot of questions on both sides as to how it would all work out.
With this shift in the balance of power, the Soviets are no longer America's ally. They are now the enemy. And for the next 50 years, tensions between the two superpowers are felt beyond the capitals of Moscow and Washington, D.C., as the world is divided between capitalist and communist. Whoever can win the hearts and minds of those around the globe will emerge victorious. As this new Cold War takes shape, people begin to realize that America's victory over Japan has become a double-edged sword. The dropping of an atomic bomb, the nuclear genie has been let out of the bottle.
Well, world reaction was stunned. I mean, this is, I think, even at the time and place, a realization that it was a monumental event, even though nobody really understood what had taken place scientifically or even politically, even with respect to the war. It was unclear. But I think most people understood, and my read of the press in particular at the time was an acknowledgement that this was really big. This wasn't just any sort of military adventure whatsoever. But it's important to keep in mind that almost nobody, including the men who made the decision to drop it and the scientists who worked on the project, understood its ramifications in full. And I think it's useful to, remember Einstein, right, saying, I don't know how they're going to fight this war, but I guarantee you how they'll fight the next with sticks and stones.
Fearing the Soviets will be next, Russian scientists begin a mad rush to acquire this technology. What the United States possesses, they must equal and better it. It is unlike any other arms race in history. The end result could potentially wipe out 1/2 of the world's population, and even more. For this reason, it is vital that both nations attain as much nuclear technology as possible to deter the other from striking. As a result, rigorous testing is done on both the American mainland and on strategic outposts like Bikini Atoll.
The B-29 Dave's Dream takes off from Kwajalein to deliver the bomb, equal to 50,000 tons of TNT, while an electric metronome counts the final seconds. Cover your eyes. Now, on away!
To calm public fear of atomic power, every attempt is made by the United States government to emphasize the positive aspects of this new source of energy. Nuclear power plants are constructed across the country as a sign of progress and achievement. President Eisenhower goes to the United Nations with the idea of using atoms for peace.
The United States pledges before you, and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life.
You have to understand the atomic aircraft project as part of the pentomic era. The 1950s, late 40s and early 50s, when everything that could be atomic was being turned into an atomic thing. There was atoms for peace. There was the idea that energy would be so cheap you couldn't meter it. You wouldn't have to meter it. Anything that could be powered by the atom was to be powered.
Despite these efforts, many are still skeptical about this source of power and its deadly ramifications. These fears are amplified with the development of Project Pluto, a nuclear-powered missile designed to unleash fission fragments all over the Soviet Union. Dubbed the Flying Crowbar, this weapon is considered too extreme even for the most hawkish Cold Warrior and is abruptly cancelled. Looking at the carnage of Hiroshima and Nagasaki, numerous Americans fear this technology throughout the 1950s.
What's it like, Chaplain? First of all, one sees a very, very bright light, followed by a shock wave, and then you hear the sound of the blast, and then it seems as though there's a minor earthquake. And then you look up and you see the fireball as it ascends up into the heavens. It contains all of the rich colors of the rainbow, and then as it rises up into the atmosphere, it turns a beautiful pale yellow, and then assembled into the mushroom. It's a wonderful sight to behold.
Hoping to end these concerns, in January of 1954, the USS Nautilus becomes the first naval vessel to safely enter the nuclear realm. With an atomic reactor powering the submarine, it can stay submerged for months if necessary, giving the United States a huge advantage over the Soviets in case trouble erupts. With this advancement, many are asking if it can work for an airplane as well.
And that's what somebody got the bad idea. Well, nuclear power, you can run a submarine, why can't you run an airplane?
Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future.
Submarines are not constrained by the same weight limitations as an airplane. So you could put a 10-ton reactor in with 100 tons of shielding, all wrapped around it in something that need only float. It's a completely different physics principle. And so therefore you have the space in the submarine for large reactors, large shielding, and large cooling systems.
It appears that what the Navy has been able to accomplish, the Air Force is going to have a harder time replicating. Despite all the doubts and skepticism, the decision to combine atomic energy with aviation is approved. Just like how the Liberators and flying fortresses that destroyed German cities mercilessly played an enormous part in winning the war in Europe, and how the constant bombardment of Japanese cities by B-29s was essential to American victory in the Pacific, perhaps a new bomber, powered by nuclear energy, will defeat the Soviets. For this reason, it comes as no surprise that many inside Air Force circles are eager to have a plane powered by the atom up in the skies as soon as possible. Across the Atlantic Ocean, the United States Navy hopes the same Anglo-American cooperation that produced the P-51 Mustang can result in their own version of a nuclear aircraft. Looking for the biggest plane Britannia can offer, both countries study the possibility of converting the gigantic Saunders-Roe Princess flying boat, a plane whose time has passed, into a device given its second wind by nuclear power. A key advantage of this concept is its range. Just 1 pound of uranium-235 is the equivalent of over 250,000 gallons of jet fuel.
With the end of World War II and the start of the Cold War, they now needed a bomber that could reach the Soviet Union from the United States. A nuclear-powered aircraft would not be limited by a fuel load, so it was desirable from that point of view.
With 30 million horsepower, theoretically, the aircraft could be up in the skies far longer than any conventional bomber in the US's arsenal.
Would sort of loiter over somewhere, US soil, presumably for days or weeks on end, possibly. Sort of simply be there as a warning.
So despite fears of nuclear annihilation, both the Air Force and the American government approved the project to develop this plane. In May of 1946, the Nuclear Energy for the Propulsion of Aircraft, or NEPA, is created, where in the secret atomic city of Oak Ridge, Tennessee, the first stages of development begin. Looking for a company to start testing, Washington goes to one of its very best, Convair, makers of the massive B-36 Peacemaker. They are awarded the contract to begin designing their version of the atomic-powered plane, which after more than a decade of research and development, they dub the NX-2, an aircraft that looks eerily similar to North American Aviation's B-70 Valkyrie. The question is whether they'll use a B-36 or the new revolutionary jet-powered B-60 to begin their preliminary tests. An act of divine intervention makes this an easy decision for Convair when a tornado rips through Carswell Air Force Base, damaging a fleet of peacemakers. With little to lose, it is after this natural disaster when the choice is made to repair one of the B-36s, named the Crusader, and turn it into a nuclear-powered bomber under the Plan X-6. with the General Electric Corporation chosen as the company to build its reactor.
The U.S. Air Force had a nuclear reactor installed aboard a Convair B-36 bomber. The nuclear reactor did not fly the aircraft. It had its own engine that was simply there as an experiment to see, for example, the thickness of shielding required to protect the crew from long-term exposure to radiation.
A key roadblock in the plane's development comes from the radiation it will emit. Anyone standing within 100 feet of the core reactor unprotected is in store for a lethal dose of radioactivity. On land, nuclear power plants are shielded by more than 6 feet of concrete. In the skies, however, this shielding is too heavy for any aircraft, including the B-36, to sustain.
The single largest problem with an atomic-powered aircraft is that a reactor requires much shielding. Roughly for every ton of reactor, you require 10 tons of shielding. This was the case in the NV-36 program. A relatively small reactor required a cockpit shielded with 12 tons of lead and lead crystal glass just to protect the crew from the radiation emitted by the reactor.
And for it to be economically feasible, it must be able to carry a payload bigger than the B-52. For nuclear aviation to become reality, these barriers must be overcome by its designers. With this in mind, Convair's still unbuilt NX-2 places its pilots and crew far away from the reactor, hopes that less shielding will be required. But even if this is accomplished, there are still questions surrounding the heat generated on board the plane. Producing more radiation than a nuclear power plant into such a contained space has scientists worried that the intense temperatures are going to melt away the aircraft's interior.
There was no real way at the time to fix these problems, much as there isn't now. The shielding still grossly outweighs the reactor, and it turns out there's really no need for it.
Just like the Navy and its Princess flying boat, the Air Force is slowly realizing that the plane and the atom don't mix. Adding to these problems is many people's fear with all things nuclear. With the possibility of an entire city being wiped out with the flip of a switch, there are grave concerns over what happens if the plane crashes. If a hot reactor falls on a heavily populated area, the civilian casualties could be enormous. With this in mind, every precaution is taken when the NB-36 is sent out on a test flight.
We had a B-50 as a chase airplane to follow us in flight. Then they decided if we had to, for instance, an accident, what were we going to do? Well, they decided we're going to have some paratroopers to follow us down. We had C-19 to carry paratroopers. And we landed. All of this was secret.
Eventually, for a number of reasons, safety, cost, practicality, the nuclear-powered aircraft never got off the ground.
With this concept all but dead, it is miraculously brought back to life when a report surfaces that the Soviets are building their own version of an atomic-powered plane, in the form of a modified Tupolev 95.
One of the big pushes for this project happened after the NB-36 had stopped flying. In December 1958, the very important magazine Aviation Week, now called Aviation Week in Space Technology, published an editorial with photographs that they said were of an atomic-powered aircraft being flown in the Soviet Union. They had these drawings that even showed the big red stars on the side of the aircraft. Turned out to be a complete falsehood, a complete lie, and it's now thought that it was put out by the contractors and the Joint Committee on Atomic Energy, who were trying to push the atomic aircraft program through Congress and to force the U.S. Air Force to accept it.
Many of the cutbacks have not been justified. I would not want to condemn all. I know one which I regard as very damaging indeed, the cutback and the stretch out of the atomic airplane program. If our technicians were permitted the money and the authority to go ahead, they could fly an atom plane next year. Under the Take It Easy program of the administration, however, We are not scheduled to fly an atomic plane before 1964, if then. I doubt if the Russians will wait that long.
Afraid of another Sputnik, the American government assures its people that with each passing year, a nuclear-powered aircraft becomes more of a reality. While behind the scenes, its designers know the project is impossible to achieve. One major blow comes from President Eisenhower, who fights to end this plane before it consumes hundreds of millions of dollars more in appropriations. But perhaps the biggest nail in the NX-2's coffin comes from a Boeing -80 prototype.
In 1957, the last year that the NB-36 was flown, the U.S. Air Force introduced its first KC-135 tankers. 3 years later, they had 400 of these aircraft, servicing as airborne refueling stations for B-52s. They could now reach any part of the Soviet Union from the United States without landing. The idea that you now needed a reactor to do this was over, and the U.S. government realized the project was essentially dead because they already had the bomber force that they wanted.
With KC-135s and B-52 Stratofortresses, by the end of the 1950s, patience is wearing thin for a nuclear-powered bomber. After spending more than $500 million, and with no end in sight, the project is now on the chopping block. As one politician is overheard saying, it has been marked by a lack of well-defined objectives and by administration indecision. The optimism of the late 1940s and early 1950s has vanished. And when a Defense Department official tells the media that the plane's price tag will be over $10 billion when finally completed, the NX-2's days are numbered.
The world is very different now.
In 1961, as the Eisenhower era ends and John F. Kennedy is sworn into office, the project receives its final nail in the coffin when the aircraft, like many other Cold War creations, is terminated.
At the end of the day, heavy atomic reactors don't really belong on aircraft, and aircraft with refueling can reach their targets anywhere in the world. A reactor was simply found unnecessary to do the job the U.S. Air Force wanted to do.
Like many other Cold War concoctions, the atomic-powered plane represented thinking big. During a time when many thought that nuclear energy was the future for transportation, it was almost inevitable that an endeavor of this magnitude would be undertaken. With America and the Soviets on the brink of complete annihilation, aircraft like these were given the go-ahead, despite its impossibilities. In the end, the atomic-powered aircraft became the quintessential example of a military-industrial complex run amok, where profits were placed above people, and where Convair was placed above common sense.
In the 60s and 70s, two American jetliners dominated the world airliner market. They were the Boeing 707 and the Douglas DC-8. One, the iconic 707, even had a popular song written about it, which became an international hit. Both airliners used a similar modern swept-back wing and four-jet layout that was considered extremely advanced for passenger planes at that time. As this duo of American commercial successes did so well, it is often overlooked that a third U.S. company, Convair, had also entered the fray, and its airliner might have been the fastest of them all. One of the most common expectations for jet aircraft is that they are fast. Though jet airliners also fly smoother, higher, and are quieter than other passenger planes, their most powerful feature of all is that they are faster. So it is perhaps logical to assume that in the competitive world of airlines, the fastest jetliner would also be the best. And if you were the Convair Aircraft Company, which were equipping the U.S. Air Force with both fighters and bombers that could fly at twice the speed of sound, it is also a reasonable assumption that their jetliner offering would indeed be the fastest in the air. The 990 Coronado. She was the most beautiful airliner of her time, and certainly the fastest. Ron Strauss recalls the 990's phenomenal speed flying in and out of Berlin for modern air transport.
When we flew the corridor in Berlin during the Cold War at 10,000, the Russians controlled the airspace. So we had to be down before the boundary. Lots of times on descent, we'd get the 990 up to 0.912 Mach, which was really fast. In fact, it would get going so fast that we'd get a vibration in the fuselage, and lots of times it would suck the nose gear doors open, so we'd just put the gear handle in the up position that repressurized the landing gear, and we'd go that way until we crossed the boundary.
The 990. She was not only fast, she simply made her competitors, the 707 and the DC-8, look just bland. Although she almost bankrupted her maker, the giant Convair, with the largest write-down in U.S. history. During World War II, numerous aircraft companies excelled in designing different types of warplanes. Although in America, most four-engine land-based planes originated from just 3 companies, at least when it came to quality and quantity. They were Boeing with their B-17 and B-29, and Consolidated with their B-24, all 3 of which were heavy bombers, and Douglas with their C-54 large transport. After the war, Americans were eager to indulge in more leisurely pursuits, and they began consuming a plethora of new technologies and products. Instant cameras and microwave ovens brought the promise of a more carefree future. The airlines and aircraft manufacturers recognized that travel would become an important part of the lives of Americans, freed from the restrictions of rationing and the obligations of war. Aircraft that had delivered death were suddenly delivering passengers to sunny destinations. Post-war, the C-54 soon became known as the civilian DC-4, followed by the DC-6 and the DC-7, in an ongoing stream of stretched but excellent passenger planes. The B-29, after conversion to a military transport, the Stratofreighter, later saw airline service as the Stratocruiser. This was a useful airliner, although it never enjoyed the success of the Douglas propliners. Another interesting post-war airliner development was Lockheed's superb Constellation airliner. Though it had almost been overlooked in wartime production, it re-emerged as a peacetime winner. In this period of transition, Consolidated, which soon became Convair, seemed to abandon large propeller transport aircraft, with the exception of a single example, the largest type ever made, the experimental XC-99. This monster proved that extremely large aircraft could be made, although only one ever was. So 3 proven U.S. propeller-driven airliners came to dominate the post-war civilian market. The extremely successful Douglas series of C-54s, which always seemed to be getting longer, Boeing's less-than-stellar Stratocruiser, and Lockheed's revitalized Constellation. For a decade, these sturdy types led the world in establishing passenger air transport for business and pleasure, and to an extent never previously dreamed of. These mainstays of the era's airlines were all straight-wing types, and so too were their military counterparts. Even the first-generation post-war fighters and bombers, many of which were jet-powered, shared the same cruciform shape as wartime propeller-driven types. Aircraft like the six-engine Martin XB-48 would have been typical of the time. Then, suddenly, all that changed. Allied countries gained access to advanced German designs, including a number developed in their 1,000-kilometer-an-hour wind tunnels. Within this cache of advanced data were conclusive facts that proved aircraft could fly safely, much closer to the speed of sound, by using the assistance of a swept-back wing. However, there were risks with the swept-back wing, risks the military were prepared to take for more speed, but it was still a tough sale. Boeing was one of the main champions of the swept-wing concept. Their XB-47 Stratojet had both wings and tail sections fully swept,